We're up to lesson 32, section 8.3, vectors, and we'll continue our discussion with these airplane problems. In this case, though, instead of the parallelogram method, we'll be solving them using the vector method. So the problem looks exactly the same as it did in lesson 31. There is actually no change in the actual problems. It's just the method we're going to use. So airplane with a given airspeed and a given direction, and there's a wind with a given speed and a given direction. And we're going to approximate the true course and ground speed of the airplane. And so these will be the same examples we had in lesson 31. The only difference is we're going to be using a vector method instead of a parallelogram method to solve them. Little refresher, all angles start due north and open clockwise. So 0 is due north and we open to the right. Due east is 90, due south is 180, due west is 270 degrees, and then due north is back up there. Vector P represents the plane, vector W represents the wind, vector R represents the resultant. That's the true course and ground speed. And then you notice we have some equations down here. The resultant is equal to the plane plus the wind. But then if you just do a little algebra, you'll find that the plane is equal to the resultant minus the wind, and you'll see that the wind is equal to the resultant minus the plane. And I think that'll make more sense as we get going here. So the basic equation is that the resultant is equal to the plane plus the wind. So the wind and the plane are going to be vectors, x and a y, and we're going to add the x's, we're going to add the y's, and we'll come up with the components, the horizontal and vertical component, the x and the y, of the resultant. Now the true course hasn't changed, it's the real direction of the plane. The ground speed hasn't changed, it's still the real speed of the plane. The only difference is we're going to use inverse tangent to find the true course, and then we're going to basically use Pythagorean theorem to find the ground speed. Now, because it's a vector method, x and y's, remember we're starting due north and opening clockwise, so our quadrants change a little bit. So now quadrant 1 is the same place, but quadrant 2 then is going to be 90 to 180. Quadrant 3, you can see there's 180 to 270, and quadrant 4 will be up there 270 to 360. So when you're in quadrant 1, both x and y are positive. When you're in quadrant 2, the x is negative, the y is positive. When you're in quadrant 3, x and y are both negative. And when you're in quadrant 4, the x will be positive and the y will be negative. So this problem should look familiar. Airplane with an airspeed of 300 miles an hour is flying in the direction of 60 degrees, and we have a 50-mile-an-hour wind blowing directly from the west, and we're going to approximate the true course and ground speed of the airplane. So let's sketch it out, and again these angles are coming from due north, so the plane is the blue line there, and it's got 60 degrees due north. And then we've got the wind down there in a blue line, and it's coming from the west at 90 degrees. And that's 90 degrees due north. And the resultant is somewhere in the middle. And we want to find the length, and we want to find the direction of the resultant from due north. So we know the angle is going to be somewhere between 60 and 90, and it's going to be some combination of the wind and the plane for that length, or that speed, the actual ground speed. So we need the horizontal and vertical component of the plane and the wind. So we take the speed times the cosine of the angle and the speed times the sine of the angle to get the horizontal and the vertical component of the plane. And we do the same thing for the wind. So you pull out your calculator, you take 300 times cosine 60 and 300 times sine 60, and you get 150, 259.8. That is the horizontal and the vertical component for the vector that represents the plane. Do 50 times cosine 90 and 50 times sine 90, and that is the horizontal and the vertical component for the wind. And then we add the x's and we add the y's. We add the horizontals and we get 150. We add the y's, the verticals, and we get 309.8. That's the horizontal and the vertical component of the resultant, the red line. Now to find the length, or the ground speed, we square the x, square the y, add them up, take the square root, and we end up with 344.2 miles per hour. That represents the ground speed, or the length, of our resultant, which is represented by the red line. Now, to find the true course, we use tangent. And tangent of theta is equal to y over x. So tangent theta equals 309.8 divided by 150. And then we do inverse tangent of that. So we do the inverse tangent of 2.0654. and we end up with 64.2 degrees. Now, I don't have to add 980 or anything like that because we knew this was a quadrant 1 vector. We had a positive x and a positive y, which is quadrant 1. Inverse tangent returns in quadrant 1. 64.2 degrees is our true course. So we end up with a ground speed of 344 miles an hour and a true course of 64 degrees. And this is the vector method. And so we're finding the horizontal and the vertical component of the plane and the wind. We're adding up the x's, we're adding up the y's, and we're getting the horizontal and vertical component of the resultant. And then we square the x, square the y, add them up, take the square root, and we end up with our ground speed. And we do inverse tangent to end up with our true course. You do concern yourself with which quadrant the resultant is in when you do that inverse tangent, because if it's in quadrants 2 or 3, you're going to have to add 180 degrees onto that inverse tangent. If it's in quadrant 4, you'll have to add 360 degrees onto it. And we'll have some more examples like that. Well, here's a similar problem. Airplane with an airspeed of 350 miles an hour is flying in a direction of 210 degrees, and we have a 40 mile an hour wind that's blowing directly north. And we want to approximate the true course and ground speed. And again, this is a similar problem that you had in the previous lesson. This time we're going to use the vector method. We're going to find the horizontal and vertical component of the plane and the wind. We're going to add them up, and that'll give us the horizontal and vertical component of the resultant. Well, these angles are coming from due north. So the plane, you can see that's in blue down there. That's 210 degrees from due north. So that's about, what, 30 more degrees there beyond 180. The wind, I stuck that in there. You can kind of see where it's going straight north there, is at 0 degrees or 360. I'm going to use 0, but you could certainly use 360 degrees if you wanted to. They both represent due north. Now, the resultant is going to be there between the two. I'm not actually sure where it's at, but it's going to be somewhere between the plane and the wind. So we need to find the horizontal and vertical component of the plane. So we do 350 times cosine 210 degrees, 350 times sine of 210 degrees, and we have to find the horizontal and vertical component of the wind, so we do 40 times cosine 0 degrees, 40 times sine 0 degrees. So you pull out your calculators, you take 350 times cosine 210 degrees, you get negative 303.1, 350 times sine 210 degrees is negative 175. The cosine of 0 is 1, so 40 times 1 is 0, or is 40. And the sine of 0 is 0, so 40 times 0 is 0. And then we add them up. You add your x's, you add your y's. You're adding your horizontal components, and you're adding your vertical components. And so now we know the horizontal and the vertical component of our resultant is negative 263.1 comma negative 175, which is a quadrant 3 vector. So now I want to find the ground speed of the resultant. So I square the x, I square the y, I add them up, and I take the square root of it, and I get 316.0 miles per hour. That's the length of our resultant. Now we want to find the true course, and that's, again, from the north. So it's bigger than 180, it's less than 360. We can pretty much assume that. So I do inverse tangent. I take the tangent of theta is equal to y over x. So that's negative 175 over negative 263.1. And I do the inverse tangent of 0.6651. Now I'm going to add 180 degrees onto this. I have to add 180 degrees onto it because it's in quadrant 3. An inverse tangent of a positive would return a quadrant 1 angle. And in this case, you can see it does 33.6 degrees. I add 180 degrees to swing it over to quadrant 3, which is 213.6. And we'll round that off to 214 degrees. That's the true course. From the north, you open to the right, 214 degrees. So we ended up with a ground speed of 316 miles an hour and a true course of 214 degrees. And again, this is this vector method where we find the horizontal and vertical component of the plane, and we do the same for the wind, and we add them up. Now, what happens, though, if we don't have the plane and the wind? What if we have the resultant and the plane or the wind, and we want to find what's missing? Well, we'll have to use subtraction. Well, now we have an airplane pilot who wishes to maintain a true course in the direction of 300 degrees with a ground speed of 450 miles per hour, and we give you the wind is blowing directly north at 60 miles an hour. So now we're giving you the resultant and the wind, and we want you to approximate the required airspeed and direction of the airplane. So we're giving you R and W, and we want to work backwards to find P. So the resultant is at 300 degrees from due north. The wind is at 360 degrees from due north. You could say 0 degrees. I'm going to use 360 this time. So for the resultant, we're going to do 450 times the cosine of 300 degrees, 450 times the sine of 300 degrees. For the wind, it'll be 60 times cosine 360, 60 times sine 360. Get out your calculators. Now the resultant, therefore, has a horizontal component of 225 and a vertical component of negative 389.7. The wind has a horizontal component of 60 and a vertical component of 0. We're working backwards to find the plane, though. So the plane is equal to r minus w. So we have to subtract here now horizontal and vertical component of the plane. And we found that through subtraction because, again, r is equal to p plus w. So therefore, p is equal to r minus w. So now I want to find the airspeed of the plane. So we square the x, we square the y, we add them up, we take the square root of it, and we get 423 miles per hour. Once we have the horizontal and vertical component of the plane, we do the same thing to find its magnitude. In this case, that's going to represent its airspeed, or what the pilot's attempting to do. And now we want to try to find out what angle did the pilot start the plane out at. And notice that the horizontal and vertical component here, we've got a positive x and a negative y. That tells me that the plane is in quadrant 4. And when the plane's in quadrant 4, we do inverse tangent. We have to add 360 degrees. So we do the inverse tangent of y over x. That comes out to be negative 67.0527 degrees. Because it's a quadrant 4 vector, we have to add 360 degrees to swing it around to 292.9 degrees, or 293 degrees. Again, go back and look at the plane there. You see that it has a positive x and a negative y. That's quadrant 4. And again, because we've rotated the quadrants, quadrant 4 is in the upper left with these airplane problems. So just do inverse tangent, add 360, 293 degrees. So we ended up with an airspeed of 423 miles an hour in the direction of 293 degrees. And this great thing about this vector method is once you have the horizontal and vertical component, you can have the worst drawing in the world and you can still get away with it. Because you square the x, you square the y, you add them up, take the square root of it, there's your magnitude, there's your speed. Do inverse tangent, and you can find the angle. Now whether you add 100, do nothing to it, or add 180, or add 360, it all depends on which quadrant your resultant or plane or wind happens to be in. All right, good luck. This concludes lesson 32. I would like for you to use the vector method to solve all the problems in this lesson. And this is going to be a similar homework to what you had in lesson 31, where we used parallelogram method to solve. But now I want you to use the vector method to solve all of them, because I want you then to make a decision which one you like the best.